Okay, first I'd like to introduce Pradeep Dubey. He's a senior Intel fellow and a director of the Parallel Computing Lab at Intel Labs. And then also we have Vipin Chaudhary, who is the Kevin Cranston's Professor and Chair of Computer and Data Science at Case Western University. And he's also worked in academia, industry, and government. And he's also a computer science engineering graduate from Kuala IIT. So we have a lot of slides, we have some Q&A, we're going to go fast. So as Ashish mentioned, we have a monthly webinar series through the QEDC. The QEDC was set up by the US government. It's the equivalent of the Semiconductor Consortium, so that the United States stays in the forefront, and also it's partnering with foreign countries as well now. And we came to the conclusion that we should probably start having these monthly webinars. These are actually very popular. Leading companies that are in quantum are all a part of this. We have about 300 attendees on each webinar. You can find it on YouTube, Quantum Marketplace. It's also public to sign up to attend the webinars. So just to give you an idea, we just ran a series in quantum computing. So the first one we ran was actually called Untangling Quantum Computing, to make sense of it, because it's very confusing. So we had Deloitte, Accenture, BCG. We had them there because we asked them, what are you advising your Fortune 500 clients today in quantum computing? And then also we had AWS, IBM Quantum, and QCI, which are all heavy in quantum computing. It was a very popular webinar, lots of great feedback. Then we decided to do software for quantum. So we had 3 leading quantum software companies, QCware, Zapata, and Qunasys. And then also Xanadu and Quantinuum, which are quantum computing companies, but they also have a software stack product. Then we had 2 quantum computing series in hardware, 6 companies each here. We're covering very many different technologies of quantum computing, also very popular. You can see them all on YouTube Quantum Marketplace. Okay, so what are some trends? So people ask about use cases. There's already over 100+ use cases identified. I'm not going to spend a lot of time going in this slide. It's courtesy of BCG, Boston Consulting Group. One thing to highlight, though, is the early work that's done in materials and chemistry, and as well as machine learning, is very promising, even with the noisy quantum computers that we have today. Very promising work. I'm not going to spend too much time here. Vipin actually is going to talk a little bit about how he envisions the software stack in quantum. This is from David Shaw. He's defining what a quantum stack could potentially morph into. Another thing that's a bit of a misnomer, some people think that quantum computing may completely replace classic computing. That's not the thinking right now. At least the thinking right now is we have very good high-performance classic computing today, but quantum computing, as Ashish was pointing out, can really help solve those tougher polynomial problems. And really, when you bring them both together, which AWS offers today on their cloud, you get the best potential outcome. So really, a lot of people a lot of companies took too long to adapt to AI and paid the price and had to catch up. One of the thinking here is, sort of the universal thinking is that with quantum computing, if you don't get in early enough, you don't have to get in a big way, but if you don't get in early enough, you might be having a real hard time catching up when this becomes a thing. All right, Vipin. Pradeep.
Thank you, Mark. Can you hear me? Yeah.
Yep.
Next slide. So the quantum promise, in our lab we have a focused effort on understanding the promise of quantum, right? Where it can be helpful and where would be the early gains. So first let's start with the problem definition, right? There clearly are problems where classical computing today is way off, and that's one of them. This is just simple spectra. You have wavelength here, and you could have excitation or whichever energy on the y-axis. And you can see it's a very simple, sorry, previous one still.
Yeah, okay.
Simple molecule phenyl radical, not very complex, but see the blue and red are the best that supercomputer can do. And the experimental results are the dashed one. There's a big difference between experimental result and the best supercomputer can do. That's the problem we're trying to solve. And this problem gets worse when you're talking more complex molecules. So go to the next slide. And as you can see, the side ones are fine, but the transition ones, right, that's the more complex ones, if you remember from your chemistry, the best algorithms are there. For the side ones, we can do more complex molecules like 30, 40 atoms. For the transition ones, we can barely do 2 or 3, and the results after that are hopeless from the classical computing. This is where naturally, inherently, quantum has an advantage. Okay, that's why we are focused here on chemistry. Now, what happens? Besides that, there are clearly very many NP problems, NP hard problems, right? And there's no shortage of those. In fact, the pioneering work in this case was done by the famous IIT Luv Grewal, right? Where we clearly show that, yeah, the speed up advantage from n versus square root of n quadratic advantage, right? And we are moving here from quantum solvers to quantum heuristics. And you can see that there is in principle advantage of 2 types, time to solution or quality of solution, okay? And quantum clearly has, but the realized speed up is still to be understood better. And I'll show you some example. Next slide. So the work we did, this is our work just 2-3 years back. And we were trying to bust the myth that quantum, that with 30, 40 qubits, you'll go past the supercomputers. No, you need hundreds closer to thousands of qubits, logical qubits, which means millions of physical qubits, before you can see a crossover. This is a simple max cut 3 regular graph problem. And you can see where clearly the slope of quantum is better as the problem complexity grows compared to the classical, which is at the bottom. But it's still classical, this is time to solution. The classical is significantly better. Now we pick a 250 qubit, and just last month, right, within 3 years, this research came out from Argonne and few people, which already improves both classical and quantum. And now you can see the gap, quantum is a dash line, and classical, the best case are those 2 magenta and blue lines at the top. And you can see quantum is in between. It's not clearly above it, it's not clearly the better yet, right, but it's in that noise. So even with few hundred qubits, we believe it will take few hundred qubits, but we could have an advantage for such problem. This is not a 100,000x advantage, but 5x, 10x, which is still significant. So moving on to the next slide. So what our lab is therefore focused on, we are looking at the full stack. We want to involve people and get engaged with people who can think such things. And how do we engage them? How do we focus so that we really maximize the potential of quantum in scheduling problems and chemistry problems? And how do we do it, right? So let's go to the next one. What we have done, therefore, is created a software stack. That's really an invitation to all of you, those of you who are interested in engaging us, right? That how can you get going for such problems? We are making it much simpler for people to engage. So from MATLAB, you can get qubit. So we have come up with a compiler IR. So you only think MATLAB, but you spell out these problems, and we will do rest of the work. And now you can begin to engage quantum simulator. That's our very first quantum simulator industry came from us, runs on supercomputers today, QHipster, and we keep improving it, and how we can get more references there on each file for you to dig deeper.
Thank you.
Okay, well, thank you, Pradeep. Thank you, Mark. You covered most of the prerequisites that I needed. So as you heard, quantum computers are already existing, but they are what we call NISQ, which stands for Noisy Intermediate Scale Computers. Right? It is that error or the noise which limits how big quantum systems you can build. So this is sort of reminiscent of how the classical computing sort of evolved. Right? We had technology cost issues with trying to build very large scale shared memory systems. And as we know today, we've transitioned to clusters, which are essentially clusters of small shared memory systems. And more recently, now we've started adding accelerators to them. So they become heterogeneous clusters. So in this project, our hypothesis really is that you are going to have a cluster of heterogeneous NISQ systems. Right? We contemplate that the progress in quantum computing is going to mimic the trajectory that we had in classical computing. Right? And it is because of this error that causes a lot of problems with trying to program these systems to actually build these systems. Right? So what we have at the bottom there is our heterogeneous NISQ systems. You have compute nodes, you have accelerators, which are our NISQ systems. And these are akin to what you have TPUs, GPUs, and FPGAs today, right? Just the same kind. But we are going to have very small NISQ systems. And the reason for that is the error profile in smaller systems is a lot better. Everyone talks about building a 1,000,000 qubit system, right? Their error rates are just tremendously bad, right? logically are very small systems relatively. At the high levels there, on the top we have applications. Clearly we want to target large applications. We won't be using these HPC systems otherwise. Now, large applications, you're going to have specialists who are going to figure out which portion of the application is going to be done by regular computers, which portion by the quantum computers. And you are going to then use standard parallel programming stuff to program the classical computers, and we are going to break the large circuits that we have, quantum circuits, into smaller chunks, just like in parallel programming, and then try and allocate those to the system. Note we have some sort of instrumentation. These systems, quantum systems, are very error prone. The error profile changes over time. It is different for every system, so you got to instrument that. Based on that, the runtime system is again going to tell you how you want to partition this. So really what we are trying to build is an open source full stack platform which is potentially independent of the hardware that you're going to use. Of course, we have to work with the vendors so that you get the hardware interface. But what this really does is it opens up such systems for people to play with, to develop applications, and to also even change such platforms. You can envision high school students who are going to now use these systems, develop innovative applications, right? And that is going to lead the way to some killer apps. Now you might wonder, high school students. Well, lots of high school students today are already programming quantum systems on the cloud. Right? So the goal, that has to happen a few things. So the goal really is, maybe I'm too close here. The goal really is that we want to be able to make such platforms easily available to the masses. And it is, in my opinion, going to revolutionize how quantum computing is going to be used. I think it's not a question of if this will happen, rather when it will happen.
Yep. Thank you. Thank you, Vipin. Okay. So let's start with Pradeep. So what is the most common misconception potential users have about quantum computing that you find?
Yeah, I already addressed two of these. The first common misconception was that all we need is 30, 40 qubits and then we'll go past every supercomputer on the planet. That's already debunked. And the second misconception is that you'll get that you'll get 100,000x speed up. Not true, right? And 10x speed up is huge, right? So it's for a certain class of problem, and it will happen in a hetero sense. Part done on classical and then of refinement, and then some part happens here. So you have to be realistic. So that's really the most common misconception, and you often see in popular press this all the time,
right,
including
a lot of hype.
last
a lot
week.
Of hype. Yeah. Vipin.
So I'll give you a perspective from what the students ask, computer science students. Oh, well, can I solve NP hard problems now easily, right? The answer is no, right? You can't solve problems which you couldn't with classical computers easily. You can potentially solve them faster, but that's where it is.
Yeah.
Great, thank you. Okay, so Vipin, where should quantum computing live in a... You guys are too close.
Let's split out a little.
So where should it live where should quantum computing live in a company today? R&D, innovation, or in IT?
Well, clearly it's not in IT yet. I think it still will be in the R&D. And I would suspect it's going to be in R&D for the next 5 to 10 years. And I think we'll start seeing enough innovations in the next few years. And Pradeep already alluded to some of the applications in quantum chemistry, which are going to be the applications which are really going to have real world impact within that time frame. So I would say continue with R&D, be involved, and within the next decade or this decade, you would get to innovation.
Yeah. So thank you, Vipin. So Pradeep, where does it live in Intel?
Oh yeah, so we have two different places where quantum resides. One are people who are actually building qubits, and remember we have focused on a certain type of qubit we believe friendlier
and
to our
that's kind of been in the public a little bit too, right?
So friendlier to our technology, right, where we can actually scale and very miniaturize spin qubits where the information encoded in the rotation, right, in the spin, right? And so that's one part, right, where and the biggest problem there is the input output and building the machine. And remember, that's why we focus on some of these NP problems, where the input output is manageable, like the graph problems, right? That's a big problem for quantum. Now the second part, second place where it resides is the software and application stack. That's where most of my lab's work is, right? And so there are two different things. One is somehow building it, but quantum is a hard problem. We typically talk about software, hardware, co-design in the parallel computing world. Here you're talking about software, hardware, and all the way device co-design. The application algorithm is designed with a core design in mind all the way to the very bottom, right? So it's a difficult co-design problem, but yes, it resides two places. One, how do we bring it to more people, simplify the stack, find more applications, and the other is how do we design more and more less noisy qubits.
Yeah, one quick question listening to both of you. So you're both highly published in this area, right?
Say again?
You're both highly publishing in this area, right? So Intel's a big company. You're public about you're working on this and it's working. So it's real, right?
Yeah. Oh yeah, I mean we have, I put references on each page, right, in each slide, and many of them are our publications. So yeah, we are heavily publishing in this area. This is one of those areas where we have to engage people and go out and have discussion much more than ever before.
Yeah, yeah, and Vipin, you're doing some leading research with NSF and others in software, right?
Yes.
Awesome, awesome. Any questions from the audience? Yes.
Yeah, a very good session. A very specific question. How do you think advances in quantum computing going to influence a wider adoption of cryptocurrencies, which also require a huge amount of computing power? Are these two fields coming together? Your views, thoughts, or maybe your vision around it. Thank you.
Take it?
Oh, go ahead.
So I think if I can repeat what you were asking, it is how is the convergence of high performance computing and quantum happening?
No,
cryptocurrencies. So that whole world which requires a huge amount of computing power.
Yes.
And quantum computing. High performance computing and crypto has converged already. But quantum computing can probably make it much more widely adopted because computing is a big challenge in that area. So wanted to hear your thoughts and vision around it.
Right. So there are two types of cryptocurrencies, right? One is what we would say digital currency. The other is the Bitcoin type. I'm personally not a fan of the Bitcoin stuff, right? But yeah, if you need to do computing of that kind, yes, quantum computers are very ideally placed to solve those kind of problems. So the factoring problem, right? That is very nicely solved by quantum computers. In fact, that really causes all the excitement within the government that is going to break all the codes, all the security that you have. And that is a leading driver for the governments to invest in that. But I think that is a little further away than some of the quantum chemistry applications which are going to be more impactful for all of us.
Another question? Thank you for that.
This is for Pradeep Dubey. You mentioned Luv Grewal. He's my classmate from kindergarten, IIT entrance topper. Can you tell me what you're doing with his research or algorithms?
I mean, I learned watching his video. He still records. By the way, I highly encourage you. I was just discussing it with Alok. So look, we are not actively working with him. At one point we did, and in fact he cites that paper in his talk. But at this point, those are like I said, our primary focus is in these, not in the chemistry and the search problems, right? So that's where the fundamental work that he did. I mean, there were two fundamental work. One was the factorization and his work to actually show that you can go get a real quadratic speed up, right, for a class of problem, an unstructured search problem. So how do we do this and how do we actually realize this? One of our two focus areas, like I mentioned, one is chemistry clearly, and the second one is that. So, but we're not directly working with him. I wish I could, right?
Another question. How about you?
What excites you about the potential of quantum computing?
Oh, I already said this is really chemistry excites me most because inherently that's what we are trying to simulate. We will with classical it's very hard, but quantum does it inherent nature, inherently quantum is better suited for those problems. So our real hope here is that we can actually design materials that nature never gave us. That's a very godlike power. Okay, it's unbelievable applications. That's where we're working with our exascale. Now we're talking zetascale. Our zetascale focuses precisely that. So quantum and zetascale are right there competing with each other. And since we do both, we are honest to both numerator and denominator. That's how quantum computing, anything gets hyped. You have a bogus denominator. We can't do that because both ours. So all these chemistry problems and drug design problem, we work with Mila directly, right, on these molecular search problems, drug design, very, very complex molecules, right? How do you do those? How do you model those? That can be your phone screen or your drug or your atmosphere, your predicting the next. It's just unbelievable applications. It'll change the world.
How about Vipin?
Yeah. So what excites me about quantum computing is really we are at this stage in the 60s or late 60s in classical computing. So we are at that stage, but I don't think it's going to take 50 odd years to get to where we are today in classical computing. That's going to be shrunk quite a bit. But there's so many computer science problems that you get to solve what we have solved. Now we are going to solve them in a very compressed fashion. So that's really exciting. It's a very fertile area to really make some contribution.
Hello. I have one more question. What do you see the role of quantum networking to scale up some of the noisiness and scale up quantum computing?
One more time, roll off.
Role of quantum networking to scale up quantum computing.
I can take that one.
Go ahead.
That's a bit, so there's a lot of debate on that, and part of it is, as Vipin had talked about with, the number of qubits that are available today, right? So there's many different quantum computing technology modalities today, right? I'll try not to go too deep in the answer here, but so of these 12 companies over here, well, not including Boston Consulting, but these companies over here are all doing quantum hardware. Some of them are doing what's called superconducting. Some are doing neutral atoms. Some are doing ion. Some are doing photonic. And part of the arguments that have been made about some of these technologies, to actually scale them up, you're going to have to connect them together. You're going to have to pass qubits between them, right? But it's very, very, very hard, and it's very, very, very early. Some people in quantum networking actually say that the market is smaller in quantum networking than quantum computing, and it's also harder than quantum computing. So it's probably going to take longer than quantum computing, but the good news is some of these quantum computing technologies are not going to probably scale without quantum networking. Now, we're also in the QEDC going to be running a series in quantum networking starting in late September through the rest of the year, 4 different ones on all around quantum networking, so be sure to tune in on that.
One question. A lot of encryption-based cybersecurity depends on prime factoring type of problems being hard. So if quantum computing makes it easy, is cybersecurity doomed?
Well, yeah, that is what scares most people. Right? But I think it's going to take a while. You can increase the number of bits that you have. I don't think we are there as yet. Is there a potential of that happening? Absolutely. That's what people are worried, and that's why there's, nations are trying to work on these problems. These are national scale problems, and national scale investments are being made by all the governments. So yes, it does help with doing prime factorization, and that can potentially lead to those problems. Is it going to happen in the next 2 years? I doubt it.